Homogeneous differential equation. A homogeneous differential equation is one where all the terms can be expressed as a function of the dependent variable and its derivatives In other words, it's a differential equation where all the terms are of the same degree in the dependent variable and its derivatives. These equations are often solved using techniques like techniques like separation of variables and substitution. Next one. What are homogeneous differential equations? Homogeneous differential equations are those in which all terms are of the same degree in the dependent variable and its derivative and is play a crucial role in various fields from physics to engineering, and understanding their solutions is key. The homogeneous differential equations are the type of ordinary differential equation ODE where all terms involving the dependent variable and its derivatives can be expressed as a function of the dependent variable itself. Mathematically, homogeneous ODE of order n is typically of the form f of x comma y comma dy by dx comma d square y by dx square comma so on a power my by dx power n is equals to 0, where f is a homogeneous function. This means if you replace y with lambda y, where lambda is any constant, f does not change its form. These equations are often solved using substitution techniques to simplify them into separable or linear forms, making them easier to solve. Next one, basic concepts. Before we before we proceed, let's refresh some basic concepts. Order, linearity, and homogeneity are fundamental aspects that define homogeneous differential equations. Understanding these concepts is crucial for solving them effectively. He- Here are some here are some basic concepts related to homogeneous differential equations. Homogeneous function. A function f of x comma y is homogeneous of degree n if if f of if f of tx comma ty is equals to t power n f of x comma y for all t not equal to 0. In the context of ODEs, this means that replacing y with lambda y, where lambda is any constant in the differential equation, does not change its form. Homogeneous differential equation, an ordinary differential an ordinary differential equation ODE, where all terms involving the dependent variable and its derivatives can be expressed as a function of the dependent variable itself. These equations are often simplified using substitution methods. Next, Next one, order of a differential equation. The order of a differential equation is the highest order of the derivative present in the equation. For example, a first order differential equation involves only first derivatives, while a second order differential equation involves second derivatives, and so on. Ne- Next one, solution techniques. Common techniques for solving homogeneous differential equations include substitution, the separation of variables, integrating factors, and using characteristic equations. And, and next one, general solution. The general solution of a homogeneous differential equation typically involves a constant of integration or multiple constants constants for higher order equations. This constant s can be determined by applying initial conditions or boundary conditions if provided. Understanding these concepts is essential for solving and interpreting the solutions to homogeneous differential equations effectively. Next one, Substitution method. One powerful technique for solving homogeneous differential equation is the substitution method. By substituting variables and manipulating the equation, we can simplify the problem and uncover the solution. Here are some basic outline how it works. First one, identify the homogeneous differential equation. First, recognize that the differential equation you are dealing with is homogeneous, meaning all terms can be expressed as functions of the dependent variable and its derivatives. Second one, make a substitution. Let y is equals to vx, where v is a new function of x. This substitution simplifies the equation and reduces it to a separable or linear form. Differentiate and substitute. Find the first, the third one differentiate and substitute. Find the first and possibly higher order derivatives of y is equals to vx with respect to x and substitute these expressions into the original differential equation. The fourth one, solve the simplified equation. The substitution transforms the homogeneous differential equation into a simpler form, typically a separable or linear equation, which can be solved using standard techniques like separation of variables or integrating factors. The fifth one, find the general solution. Once you have solved the simplified equation, you will obtain a general solution in terms of the new function v or whatever variable you use for substitution. This solution may contain arbitrary constants. Sixth one, reverse the substitution. Finally, revert back to the original variable y by replacing v with y by x if necessary to express the solution in terms of the original dependent variable. This method is particularly used for reducing the order of differential equation and making it easier to solve. It's widely applicable to various types of homogeneous equations encountered in differential equations. Next one, advanced techniques. Advanced techniques. Beyond the basis, there are advanced techniques and approaches to tackle complex homogeneous differential equation. Will explore reduction of order, variation of parameters, and other advanced methods to broaden our problem solving toolkit. Example. First one, Laplace transforms trans, transform. This technique involves transforming the differential equation from the time domain to the Laplace domain, where algebraic manipulation can simplify the equation. After solving in the Laplace domain, the inverse transform is applied to the domain the solution in the time domain. Second one, series solution. Homogeneous differential equations can be sometimes be solved using power series expansion, assuming a solution of the form y of x is equals to sigma n is equals to 0 a power n a n x power n. Substituting into the differential equation and equating the coefficients can yield a recurrence relation for the coefficients a n, allowing for the determination of a series solution. Next one, green functions. Green functions are used to solve inhomogeneous differential equations by next one, putting it all together. Putting together advanced techniques for solving homogeneous differential equations involves a systematic approach tailored to the specific equation at hand. Here's how you might approach it. First one, identify the equation type. Second one, select appropriate technique. The third one, apply the technique. Fourth one, solve the constants. Fifth one, verify the solution. Sixth one, interpret the solution. The seventh one, generalize and refine. Eighth one, consider limiting cases. So by integrating various techniques and approaches, you can effectively tackle homogeneous differential equations of different complexities and gain a deeper understanding of the solution and properties. Next one, the beauty of homogeneous differential equations. As we conclude our journey into the world of homogeneous differential equations, we appreciate the elegance and beauty of the solutions. The ability to crack the code of these equations open doors to understanding the underlying patterns in the nature and the universe. The beauty of homogeneous differential equation lies in their elegant mathematical structure and the rich variety of techniques available for solving them. Here are some few aspects: the symmetry and simplicity, universal applicability, interplay of mathematical concepts, insight into fundamental principles, aesthetic appeal, applications in physics and engineering, etc. O- Overall, homogeneous differential equations often not not only a practical tool for modeling real world phenomena but also a source of beauty and inspiration for mathematicians and scientists alike, showcasing the elegance and power of mathematical reasoning. And thank you.